Hello and welcome to the second lecture on causal inference. We're going to start today's lecture by asking the big question, what actually is causality? So think about this for a moment and see if you can come up with a good definition. My guess is that you're going to have some trouble. And why is that? So if you think about it for a moment, you would see that causality is sort of like time and space. So it's like a fundamental human category that we use to understand other things. And it's the first principle. And so if you try to make definitions about something, so if you try to define a concept, we usually have to define it in terms of other concepts. And so if causality is the first principle, then it becomes hard to find other concepts with respect to which we can define causality. All right, so it is actually kind of tricky. And if you try to see how causality is used in everyday language, it turns out that we mean different things in different situations. All right, so let me list a few sentences to illustrate how causation can be used in different ways, in different sentences. So here are a few sentences. The soccer ball moved because I kicked it. My girlfriend broke up with me because I wasn't spending enough time with her. I am who I am today because of my mom. Gravity causes objects to fall to Earth. Down syndrome is caused by an extra copy of chromosome 21. Humans are causing climate change. Barbarian invasions caused the Roman Empire to fall. And smoking causes lung cancer. Okay, so all these sentences have a similar form. Okay, so they're all the form A causes B, where A is some object or event, B is some object or event. But in this case, the meaning is slightly different. Okay, and so let's try to see how other people have thought about causality. Okay, so causality is really important, so it's not surprising that even 2,000 years ago, philosophers have already been thinking about it. So I'm going to show you Aristotle's definition. All right, so Aristotle is one of the most influential Western philosophers. So he said that a cause is an answer to a why question. All right, so this is really broad, and this may be a little bit different from how you would think about causality, but this is how he defined it, and this theory was very influential for thousands of years. So let's see what it is. Okay, so he also further broke down causes into 4 types. Okay, so these 4 types are the material cause. Okay, so the material that an object, the object B, is made out of. The formal cause, which is essentially the form or the shape of object B. The efficient cause, which is the action that causes a change or a state. Okay, so here, if we're talking about a statue as being the object, then the efficient cause of that can be the sculptor of the statue, or it can even be the actor sculpting the statue. Okay, and lastly, there's the final cause, or sometimes also known as the teleological cause, and this is the purpose of an object. Okay, so here, one of the examples given is that health is the end of walking, or health is the cause of walking. And maybe in the context of a statue, you can say that the final cause of the statue is for the aesthetic enjoyment of other people. Okay, so most of these definitions seem a little bit strange to our modern sensibilities. And that's because the meaning of cause has changed over the years. And at least in a scientific setting, we have come to focus on the third definition, which is the efficient cause. And again, this is the change or the action of the action events or object that is responsible for a change or state. Okay. And so now let's try to see how this definition can help us to take a closer look at the sentences that we wrote just now. And let's say that if we restrict ourselves to just thinking about the efficient cause, we rule out these 2 sentences. Okay, so this might be, you might disagree with me. So this, obviously there's definitely some gray area. And let me just try to argue for why I think the sentence about gravity should not be thought of in terms of efficient cause. Okay, so gravity is a force, right? And we're trying to, by this sentence, we're trying to explain the phenomenon of objects falling to the earth in terms of this force. But if you think about it, gravity is not itself an entity. It's not an object. It is an explanation for this phenomenon. Okay, so this is sort of this is more like a description, and it's not actually a standalone entity that is responsible for the change that happens when objects fall. Okay, so you may or may not agree with me, but I'm sure that you agree that there's definitely some difference between the sentence and the other sentences. Okay, so how about the other sentences? Are there some further differences between them? Okay, so in fact, I think there are plenty. So here are some ways in which we can distinguish between them. Okay, so first is that some of them are about deterministic causes, whereas others are about probabilistic causes. Okay, so what I mean by this is that if A is a deterministic cause of B, then whenever A happens, B is going to happen as well. And if instead A is a probabilistic cause of B, then the existence of A is going to increase the probability of B happening, but it's not a sure thing. Okay, it's not deterministic. Okay, so these three sentences that I highlighted in green are deterministic causes. Okay, so when you kick a soccer ball, it's definitely going to move. Whenever you have an extra copy of chromosome 21, you're going to have Down syndrome. And I would say that humans are definitely causing climate change, and it's not increasing the probability of climate change, but it's actually deterministically causing it. Okay, and the other sentences that I did not highlight are probabilistic causes. Okay, so again, this is a judgment call. You can agree or disagree with this classification. Okay, so my girlfriend broke up with me because I wasn't spending enough time with her. Okay, so maybe this is even more of a gray area. I would say that this is, if you don't spend enough time with your girlfriend, it's not a sure thing that she's going to break up with you, but it's definitely going to make her upset, right? So it's going to increase the probability of that happening. All right, and I must say that this is hypothetical, so this didn't actually happen in reality. Barbarian invasions caused the Roman Empire to fall. I think, so this is a history question. I would argue that this is probabilistic, but you might disagree. Smoking causes lung cancer. This one, we know for sure that some people who smoke do not end up getting lung cancer at all. So smoking does not determine whether or not you get lung cancer, but it definitely increases your risk of getting lung cancer. Okay, so it increases the probability of that happening. All right, so here's another lens of trying to view these statements. Some of these statements are about instances, and other sentences are about classes. Okay, what I mean is that an instance is a specific object or event, and a class is an entire category of objects and events. Okay, so again, you can see that the sentences that are highlighted in green are about individual people or events. Okay, maybe the latter two are a bit contentious. I would say that when we say humans are causing climate change, we're referring to the entire humanity as an entity. And climate change is a singular event. Okay, it's very complex, but it's a singular event. So there are not many different instances of climate change. Okay, so I would argue that this sentence is about instances. Okay, and here are other ways of trying to distinguish between the sentences. Some of them are about single causes, some of them about multiple causes. Multiple causes means that for object B, A might not be the only cause. There might be also other causes that work together with A that causes B. And then another way of looking at these, the differences between the sentences, is whether they talk about a simple actional event or a compound actional event. Like for instance, climate change is very complex. Okay, and this means that when we say humans are causing climate change, is really, we really mean something that we really mean causation in a different sense compared to when we talk about something that is simpler. All right, and now, okay, so let's move away from how we use causation in everyday language and see how people think about it in scientific domains or other domains of knowledge. Okay, and it turns out that each of these domains has their own conventions, their own nuances of how they think about causality. Okay, so let's look at this picture. Okay, so you've never seen this before. This is a cause of death certificate that hospitals have to fill out whenever some patient dies. Okay, and so what they have to do is that they have to list an immediate cause of death on this first line here. And then if you look carefully, in the subsequent lines, they are given the opportunity to list other conditions that led to the immediate cause of death. Okay, so these are more distant causes of death. All right. But if you think about it carefully, right, there are definitely some judgment calls that go into how they fill out this form. Because patients normally, or at least some patients, come with multiple conditions, right? And it's not quite clear which of these conditions are responsible for the development of for the deterioration of their condition and leading to, and what actually leads to the immediate cause of death, or what even is the immediate cause of death itself. Okay, so there's definitely some gray area. And this is also the reason why initially there was a lot of controversy about how COVID-19 deaths were being counted, because patients who died of COVID-19, a lot of them had other comorbidities or other conditions, right? So some people argued that these people died because of these other conditions and not because of COVID-19. Okay, but physicians have their own way and culture of deciding how to fill out these forms, and so in deciding what actually constitutes a cause of death. Okay. All right, and there was in medicine, as can be expected, causation is also very important in law, for instance, and lawyers also have their own ways of deciding what constitutes a cause. Okay, so what are the takeaways from all this discussion? Okay, so first, we definitely have some intuition for what causality means, but as you saw, it's very hard to make it precise, especially because even in everyday language, we usually call the word cause in different ways. And furthermore, even in scientific fields or technical fields, people use cause in different ways as well. Okay, so these fields all have their own nuances and conventions. Okay, and even today, there's a lot of philosophical debate about what causation actually is. Right, so this is not, people have not, definitely have not agreed upon something. There's still a lot of debate that still happens. All right, so now that we know that we have to be a bit careful about the way causation is defined, let's take a look at what we're going to cover in the rest of today's lecture. Okay, so first, we're going to make a definition of causality in the context of data science. And we're going to formalize causality using the notion of counterfactuals. Okay, counterfactuals means parallel universes, right? And we're going to talk about this in a moment. All right, and then we're going to introduce randomized experiments, and we're going to see how randomized experiments build upon this notion of counterfactuals. Right, so we have to make some assumptions when we think about randomized experiments. So we're going to talk about some of these assumptions, and we're going to see some examples of randomized experiments. And then we're going to try to answer the question, what actually is the randomness behind the randomized experiments? Okay, and this is going to be pretty different from what you've seen so far in other parts of this course, or even other previous statistics or data science courses. Okay, then we're going to talk about how to do inference for randomized experiments. All right, so what actually is the the estimates that we want, and how do we find confidence intervals, how do we do hypothesis testing. And lastly, we're going to talk about some complications that can arise with randomized experiments. Okay, so hope you look forward to the rest of this lecture. So how do we define causality in the context of data science? So let's start with an example. So suppose that you have a fever and you wanted to decide whether or not to take aspirin, right? And so you might be interested in the question, what is the causal effect of taking aspirins on my temperature? So here's a very natural way of thinking about causation. So we're going to take this tablet and suppose that right now we have our temperature is, say, 39 degrees Celsius. And then after taking this tablet, in say 3 hours time, we take our temperature again and we see that our temperature is now 37 degrees Celsius. So we might conclude from that that the causal effect of taking this aspirin is a decrease of 2 degrees Celsius in body temperature. But then this seems actually not quite right, because it's not clear just from this that taking this type of aspirin was the specific event that led to this decrease in temperature. Okay, we're comparing a before and an after, but this tablet aspirin is not the only change, not necessarily the only change between this before and after. Okay, so it could be the case that even if we did not take the aspirin, just by the forces of recovery in your body, the temperature could just naturally decrease from 39 degrees to 37 degrees. So instead of comparing before and after, we need to compare two alternate universes. We need to compare the universe in which we took this tablet of aspirin with the other universe in which everything else is the same, except for the fact that we did not take this tablet of aspirin. All right, so we want to compare our states in these two universes, and then to formalize this comparison, we define potential outcomes. Okay, so in this context, the potential outcomes y1 and y0 are going to be the temperature of your body temperature 3 hours after this decision of whether or not to take the aspirin tablet. Okay, so 1 means we take the aspirin, 0 means we do not take it. And so y1 would be the temperature when you take it, y0 would be the temperature in the event that you do not take it. Okay, so these are called the potential outcomes. And then the individual treatment effect is going to be the difference between these two outcomes. Okay, but there's a problem. Okay, so we want to define, it's very natural to define causality in this way, but there's a problem. And this is called the fundamental problem of causal inference. And it is that we are only ever able to see one of these two potential outcomes, right? So whenever we take the aspirin, we cannot go back in time and not take it. And if we don't take it, we cannot go back in time and take it. Okay, so and maybe if we don't take it now, we could take it 3 hours later, but then the state of the world has changed, so it's no longer a fair comparison as well. Okay, so the upshot is that we are only ever able to see one of the two outcomes. So this individual treatment effect, which is the difference between the potential outcomes, is unidentified. Okay, so we are never able to say what it actually is. Okay, so you may see from this that this is a pointless definition. Okay, but we can actually overcome it. And this was the brilliant insight of Ronald Fisher. So what was his insight? Okay, so his insight was to do a randomized experiment. And this means that instead of just considering one individual, okay, so instead of considering just yourself, consider an entire group of individuals. Okay, so if you, instead of seeing how aspirin affects your temperature, let's see how it affects everyone's temperature. And then, apart from looking at a whole group of people instead of just one person, we are going to do randomization. And randomization is going to be our basis for inference. Okay, so this is a little bit subtle. So I'm going to say what, I'm going to spend a lot more time saying what I mean on in the latter part of today's lecture. Okay, but first, let's introduce the science table. Okay, so now we have a randomized experiment with many, many people. Okay, so it's not just you, it's a whole bunch of different people. And for every single person, we have two potential outcomes. Okay, so we have the temperature if they take aspirin and the temperature if they did not take aspirin. All right, and we can list all of these potential outcomes in this n by 2 table. Okay, and this n by 2 table is called the science table. All right, and we do not get to observe this table in practice because of the fact that we can only see one of the two potential outcomes of each person. Okay, so some of these entries are missing. Okay, so in an experiment, this is the state of the table that we observe. So now let's make some definitions. Okay, so we're going to use Z sub I to denote the treatment assigned to unit I. Okay, so unit is just maybe you can think of a unit as a person, but sometimes we do experiments where people are not the objects of these experiments, but instead units can be other things. So it could be, for instance, states or other groups, or it could be non-animate entities. Okay, and usually we think of treatment as being binary. Okay, so that's a simpler setting and seems to encompass many things that we want to investigate, but we can definitely consider treatments that are non-binary, that have more levels. Okay, so more meaning that more different, more forms. And we can also think about continuous treatments, but that's a very advanced topic. Okay, so as said before, y sub I 1 and y sub I 0 are the potential outcomes of unit I. And these are the outcomes under treatment and under no treatment, respectively. Okay, so no treatment is also called control. And for every person, we observe as an outcome y sub I ops. Okay, so this is the standard notation. And this is defined to be the potential outcome under the treatment assignment, ZI. Okay. And now there's some, so I showed you the science table just now, but there are actually some built-in assumptions in writing down the science table this way. And the built-in assumption goes by this fancy name. It's called the stable unit treatment value assumption, or SUTVA for short. Okay, and this is actually a compound assumption that has two parts. The first part is the assumption about no interference. And this means that potential outcomes for unit I only depend on the treatment assignment to unit I and does not depend on treatment assignment to other units. Okay, so in the context of our experiment about aspirin, this is saying that your temperature only depends on whether or not you take aspirin and does not depend on whether your sister takes aspirin or somebody else, your neighbor takes aspirin. And the next part of this assumption is the assumption that there are no other versions of the treatment. Okay, so here we say that we want to compare, we want to investigate the treatment effect of taking aspirin. So there has to be a single type of aspirin tablet. Okay, so we don't want there to be different brands. We don't want there to be different doses of aspirin. We want the treatment to refer to a singular dose of aspirin and a singular, well, and everything else should be the same. So same brand, same form of tablet. Okay, so if we don't have this, then the potential outcomes is not going to make it's just not going to make sense the way that we want it to. All right, so now to give you some more intuition, let's see some examples of experiments that people actually have done, or some ideas of possible experiments. Okay, so this was the experiment that actually was done. Okay, so people were interested in the effects of job training programs on employment and wage. And so here, the treatment or the intervention was whether or not a person was able to participate in a job training program. Okay, so here, participation in the program was randomized. Okay, and here, in the second example, these authors were interested in the effect of different get out the vote campaigns or different get out the vote messages on voting behavior. Okay, and here the intervention was different messages. All right, third example, the 2008 Oregon Health Insurance Experiment. Okay, so what happened was that in 2008, Oregon expanded its Medicaid, and they used this as an opportunity to do an experiment of the effect of health insurance on health and economic outcomes. And so here, the intervention or the treatment was enrollment into Medicaid, and this was done by lottery. Okay, so the lottery was the randomization. Okay, and lastly, tech companies like your Googles and Facebooks are always interested in how different versions of their app affects user engagement. Okay, so they're constantly doing all these randomized experiments, which goes by the name of A/B testing in that context. Okay, so these are 4 examples, and already we see that Sutva need not actually hold for some of these examples. Okay, so for instance, in this get out the vote experiment, okay, so what they're doing is that they're giving different households different messages, right? Different, so it could be like I forget the precise details of this experiment. So I think they gave them mailers, and some of them had peer pressure messages, some of them just had messages about civic responsibility and stuff like that. And here, if we have people in the same household as individual units, then they are going to, so whatever treatment somebody in a household receives, the other people in the household are also going to receive the same message, right? And in fact, the behavior of a person in the household is definitely going to affect the behavior of other people in the same household. All right, so in that case, Sutva is going to break down if you consider multiple people in the same household. Okay, and something similar is happening in the last example here, because if you change, let's say you change the app version for some user and they become more engaged, and he or she is going to talk more with their friends, perhaps on the same social media app, and this means that the friends are also going to become more engaged, even if they did not receive the treatment or they received some different treatment. All right. So again, Sutva is going to break down. Okay. So in both of these cases, the part of Sutva that breaks down is there's no interference portion. Okay. We're going to talk about the other part of Sutva later on, and either today's lecture or the next lecture. Okay. And lastly, let's talk about randomization. Okay. So what actually is the randomness in a randomized experiment? Okay. So contrary to the randomness that comes that you see in other areas of statistics, the randomness for the randomized experiment is not in the sampling, right? So we're not sampling from some infinite population, and instead, what is random is the treatment assignment, and this is determined not by nature, which is usually the case for statistics, and instead, this is determined by the people who design and run the experiment. Okay, and in fact, we do not sample IID. Usually what we do is what is called complete randomization. So here we fix some number n sub 1 of patients or individuals that we want inside the treated group, and then whatever's left over will be n0, and this will be the size of the control group. Okay, so we want to preserve the sizes of these two groups, and usually we want them to be the same. And what we do is that we choose a random permutation of the individuals such that n sub 1 of them are assigned to the treatment group and then sub-0 of them are assigned to the control group. All right. And so what's the probability? Okay, so you have to think about how many ways there are of choosing n sub 1 individuals from a population n individuals. Okay, so this is just the binomial coefficient n choose n sub 1. And so you're just choosing one of these choices at random. Okay, so uniformly at random. So the probability of any choice is 1 over this quantity. Okay. All right, so lastly, another way to see this is that we're just choosing n sub 1 units uniformly without replacement to form our treatment group. Now let's talk about how to do inference for randomized experiments. To start, let's introduce the estimate that we are mostly interested in. And this is called the average treatment effect. And this is usually denoted by ATE. Okay, and I just want to say that this quantity has other names as well. Sometimes people also call this the average causal effect. Denoted ACE. Okay, so just be careful with that. Different people have different terms for this. All right, so how is this defined? Okay, so this is denoted tau, and it's defined to be the average individual treatment effect. Okay, so 1 over n times sum from 1 to n of yi1 minus yi0. Okay, so a few things to note about this. Okay, so this is the average of individual treatment effects, and this is a fixed quantity. Okay, so this is not random. Why? That's because in a randomized experiment, we assume the entire sample to be fixed. And furthermore, we assume that the potential outcomes are also fixed. So remember the science table from the previous video. The science table with all the entries reviewed is a fixed object. And the only randomness is in terms of which entries we see and which entries we don't get to see. And because of the fundamental problem of causal inference, we're not able to actually identify tau. So we can only estimate it. Okay, so the name of the game in randomized experiments is about how to best estimate this tau. Okay, so that's our estimate. Now let's talk about how to estimate this. Okay, so here's one estimator. This is called the Neyman estimator, or the difference in means estimator. Difference in means. And this is defined to be tau hat. Okay, so it's denoted tau hat, and it's defined to be 1 over n1 times the sum of the observed outcomes for all units I with zi equal to 1. So this is all the treated individuals minus 1 over n0 times the sum over all of the controlled individuals of their potential outcomes, of their observed outcomes. All right, so this is the definition. And the remark is that tau hat is also the sum of the potential outcomes because of the way we set up the assumptions of our randomized experiment. Okay, so this is our estimator, and it's very natural. Okay, so we just take the average outcome over the treated group minus the average outcome over the control group. Okay, so here are the properties of this estimator. So first, an expectation, tau hat is equal to tau. Okay, so it's unbiased. Okay, so that's always a good thing. And secondly, we can compute an upper bound for its variance. Okay, so this is bounded by s1 squared over n1 plus s0 squared over n0, where, okay, so for each of these k's, k is equal to 0, k is equal to 1, sk squared is defined to be 1 over nk minus 1 times the sum over I from 1 to nk of this variance term yik minus y bar of k squared. Okay, so this is the sample variance of the potential outcomes under treatment when k is equal to 1, and the sample variance of the potential outcomes under control if k is equal to 0. Okay, and if you know what happens for when you have IID sampling, then this formula for the variance, this upper bound, should look pretty straightforward. Okay, so this upper bound is what you should expect if you were sampling IID or with replacement. But because you're sampling without replacement, there is going to be some other term that is involved here. So we are going to drop it and we get this upper bound instead. Okay, let's go ahead and prove the first of these two properties. We start off with taking the definition for the naming estimator and writing it this way. And let's change the way we write it slightly. Okay, so the sum over all of the terms of the units in the treated group can also be written as a sum over all units of the treatment indicator times yi1. And likewise, we can write the second term as a sum of all units of the control indicator, which is the same as 1 minus the treatment indicator times yi0. And hence, when I write the expectation of tau hat, I can pass through the sum, I can interchange the sum and expectation and write this as an expectation of zi over n1 times yi1 plus or minus sum from 1 to n expectation ci, 1 minus ci of n0 times yi0. Okay, and now the next step is to realize that yi1 and yi0 are fixed. Okay, and the only randomness is over the zi's. So again, we can pull these out of the expectation and we get expectation zi over n1 times yi1 minus something similar on the right, Okay, so now we just have to say what these two expectations are. Okay, so think about complete randomization. Okay, so what's the probability that Zi is equal to 1? Okay, so there's a probability that unit I is inside the treated group. Okay, so there are n individuals in total, and one of them go into the treated group. So this is n1 over n. Okay, and likewise, P is I is equal to 0 is equal to n0 over n. All right, so we can plug this into our equation. And this is going to give us n1 over n divided by n1, but now these two cancel. Right, and similarly, we're going to get 1 over n0, sorry, 1 over n times y0. And now we can collect all the 1 over n terms on the outside and see that this is simply equal to the ATE as we wanted. Okay, so that's the end of the proof that shows that the Neyman estimated tau hat is unbiased. Okay, the second property is more difficult to prove, so we're not going to do it. Okay, so just be aware that we can get this upper bound for the variance. Okay, and the next step is to now we have an estimator for our estimates. Now we want to get confidence intervals. And we also want to do hypothesis testing, but let's do confidence intervals first. So what we're going to get are conservative confidence intervals. And this is going to be by making use of our bound for the variance of the Neyman estimator. Okay, so let's first introduce a notation. Okay, so I'm going to use V Neyman to refer to this bound over here. Okay, so again, it's an upper bound for the variance of the Neyman estimator. So what we want is a sample estimate of V Neyman okay, so let's define our estimator, which we're going to denote by V Neyman hat to be equal to small s1 squared divided by n1 plus small s0 squared divided by n0, where small s1 squared is simply going to be the sample variance of the observed outcomes over the treated group. Okay, so sample variance is 1 over n1 minus 1 times this term here. Okay, so when I subtract the mean, this is going to be a mean of the observed outcomes over the treated group. Okay, so I'm summing over all units of ZR is equal to 1. And then S0 is also going to be defined in a similar manner. And so by swapping out the variance for the entire population, for the sample variance over the treated and control groups, we get this estimator of the Neyman variance. Okay, so here's the effect. The Neyman variance is an unbiased estimator. The Neyman hat is an unbiased estimator of the Neyman variance. Okay, so proof is going to be left as an exercise, but this is simply because the sample variance is an unbiased estimator of the population variance. Okay, so the upshot is that now we have a sample estimate of the Neyman variance. So Okay, one more fact, or let's call this a theorem. Okay, so under some regularity conditions, we have this normal approximation theorem. Okay, except that now, because the Neyman variance is an overestimate of variance, so this is not necessarily going to converge to a standard normal, but it's going to converge to a normal distribution where sigma squared is something that's going to be less than or equal to 1. Okay? Okay, that's because the denominator is possible overestimate of the variance. Okay, so this is the case, and asymptotically valid on the 5% confidence interval for the ATE tau is given by tau hat minus 1.96 times square root of the Neyman variance, and the upper bound is tau hat plus 1.96 times square root of the Neyman variance. Okay, so this is how we get 95% confidence interval. Let us now talk about how to do hypothesis testing for randomized experiments. So it turns out that there are two different null hypotheses that people are typically interested in. And so these are the null hypotheses that people test against whenever they want to say whether a given treatment or intervention has a treatment effect or not. So let's write these down. The first null hypothesis is the so-called Neyman weak null hypothesis. Okay, so this is typically denoted by H0n, n stands for Neyman, and this is the hypothesis that the ATE is equal to 0. All right, and then there's another null hypothesis called Fisher's strong null hypothesis, and this is denoted by H0f. And what this hypothesis says is that the ITE, the individual treatment effect, okay, for the ith unit, which is equal to yi1 minus yi0, is equal to 0 for all units I. Okay, so this is much stronger. So Neyman's null says that the treatment effect is 0 on average, and Fisher's null says that the treatment effect is equal to 0 for every single individual. And historically, there was a lot of debate as to which of these two null hypotheses was more interesting or more appropriate. Okay, so Fisher and Neyman notoriously had very strong disagreements. All right, and you can find people arguing either notion today, but in our course, and I think in a lot of the more recent literature, people tend to favor the Neyman weak null hypothesis. Okay, it's a Fisher's null hypothesis is too strong. Okay, but let's talk about how to test these two types of hypotheses. Okay, so first, to test H0n, we consider the test statistic which we're going to denote T. Okay, and this is going to be the Neyman difference in means divided by square root of Neyman variance. Okay, so this is a test statistic. And if we know that if tau, the true ATE is equal to 0, we know from the theorem that we wrote earlier that this is going to converge to a normal distribution. right? So it's going to be a normal distribution with variance that is smaller than or equal to 1. Okay, so we get some asymptotically valid conservative because the variance is an overestimate p-value by comparing t against the standard normal. Okay, so I'm just going to write 0, 1. Okay, so what do I mean by comparing t against n01? So this all depends on whether you want to do a one-sided test or two-sided test. Okay, so if it's a one-sided test, then you want to just compare it against one of the tails of the Gaussian, and then if not, you want to compare it against both tails. Let's now talk about how to do hypothesis testing for the Fisher's strong null hypothesis. And it turns out that something very convenient is going to happen under the Fisher null. Okay, so essentially, if the Fisher null is true, then we actually know all the entries and the science table. Okay, so recall that the science table is this n/2 table of the potential outcomes. Okay, and because for every unit, the two potential outcomes are the same, and we observe one of them, it means that we know the values of both of them. Hence, what we can do is to use a permutation test. So in other words, we pretend that instead of the division into the treated and control groups that we got obtained by doing our randomization, what if we did a different randomization? So the same randomization scheme, but just a different output of the randomization. And we can actually compute the ATE under a different randomization because we know all the potential outcomes. So we know the entire distribution. Okay, and so by knowing the entire distribution, we can obtain a p-value for the value that we actually observed. And this is called a permutation test. Okay, so this is very high level. I'm not going to really go into the details. Okay, so if we have time, we might do some of this and the exercises. If not, it's just something that is good to know. So it's good to know that there are these two different types of null hypotheses. Okay, and the main reason, or one of the big reasons why some people would prefer to use the Fisher null is precisely this. It's because that we don't have to rely on any large sample asymptotic theory. We can get valid p-values by just doing a permutation test. In this video, we're going to introduce Fisher's exact test, which is a test that you can use to test the Fisher sharp null hypothesis. Okay, so this applies to the setting where we have a binary outcome variable y. Okay, and here's an example. So imagine that you want to test the effect of aspirin. So the treatment Z can be taking aspirin. So whether or not a given individual takes aspirin, and Y can be whether the fever goes away. All right. And now let's draw the science table. Okay, so the science table in the binary outcome setting is just going to be a table of ones and zeros. Okay, so let me draw a suitably tall table. Okay, so recall that it's going to be an n/2 table of your potential outcomes. Okay, then some of the rows are going to be ones, some of them are going to be zeros. Okay, so it's going to be a huge table. Now, what can we do with this? Okay, so because our outcome is binary, we can summarize this table. Summarize by doing cross tabulation. And this will result in a 2x2 contingency table that would be kind of similar to what we saw in the first few lectures. Okay, so this table is now going to have 2 rows and 2 columns. Okay, so the rows are going to correspond to our outcome. So either the treatment, the aspirin fails or it succeeds. And we have 2 treatment arms. Okay, so the control group and the treatment group. And then the entry in the top left would be simply the number of individuals who did not take aspirin, so who were in the control arm, and for whom they did not recover. Okay, so the outcome is a failure. And then for the top right entry, this would be the number of individuals who get treated, but the outcome is a failure. And then analogously, we can define the bottom 2 entries in this table. Okay, so how about the column sums and the row sums? So the column sums are going to be pretty straightforward. Okay, so recall that we're doing complete randomization, so the size of the control population and the treated population are fixed. Okay, and these are going to be the column sums, and 0 and 1. And now I'm going to introduce some new notation to denote the row sums. So I'm going to call this N, let's see, N failure and N success. Okay, so now let's take the next step and assume that Fish's strong null hypothesis holds. Okay, so in this case, what happens? Then we know all the entries in the science table. And furthermore, let's look at the row sums. Okay, so NF counts the total number of failures, and N sub S counts the total number of successes, meaning patients who recover. And if the treatment, if the strong null hypothesis holds, this means that treatment has nothing to do with the outcomes at all. Okay, and so both potential outcomes and every row are the same. And so this means that the number of failures and numbers of successes does not depend on the treatment assignment at all. Okay, so in other words, when we take this contingency table, the science table, and write it out what we know now. Okay, so now we can fill in all the entries. Okay, so then NS and NF have the following meaning. So NS is simply equal to the number of rows with 1, and NF is equal to the number of rows at 0, and this does not depend on treatment assignments. Okay, so now going back to this 2x2 table, we see that the row sums and the column sums are fixed. And the only thing that can change are the entries inside the table, N00, N01, N10, and N11. And those are the numbers that depend on our randomization. Okay, and not only that, we know exactly what the distribution of these numbers are. Okay, so these numbers are going to follow the hypergeometric distribution. all follow hypergeometric distributions. Okay, so hypergeometric distribution has two parameters, n and k. Okay, and it's going to be the probability of choosing, of having R successes given choosing k items without replacement from a population of size n. Okay, so you can go look this up on Wikipedia. Okay, so for us, it's not super important. Okay, what's important is that this is going to allow us to define a p-value and a hypothesis test. Because now we have our observed counts n00, n01, n10, and n11, and we can compare them to this distribution, this hypergeometric distribution. And if the counts are very extreme compared to our distribution, then we know that the null hypothesis is very unlikely, in which case we're going to reject it. Okay, so this is maybe a slightly different logic compared to the other p-values and tests that you're used to. Okay, so this is a p-value that comes from a permutation test. Okay, so permutation, because the randomness is that we have from a randomization scheme is about permuting, just choosing a random subset of our population. We are now going to illustrate the inference concepts that we learned in the previous videos through a concrete data example. Okay, the example I chose was this paper about racial discrimination in the labor market. And this is by Bertrand and Malayanathan from 2004. Okay, so what happened is this. So the goal of these two authors was to study whether or not there was racial discrimination in the labor market. And to do so, they created a pretty ingenious experiment. So they created 4,800 or so fake resumes. And for half of them, they put names that were stereotypically white, like Emily and Greg. And then for the other half of them, they labeled them with names that were stereotypically black, like Lakeisha and Jamal. All right, so the names were randomized in this fashion. And then these resumes were sent to potential employers, and the authors then waited to see if they got callbacks from the employers for all of these resumes. Okay, so what's the treatment? What's the outcome? Treatment was race, and the outcome was whether or not the resume received a callback. Okay, so if the resume received a callback, then that is deemed a success, and if not, then that's a failure. Okay, so this is pretty ingenious. Typically, it's not quite clear how we can use race as a treatment, but they were able to do so in this context. All right, so let's look at how we can apply our techniques that we've learned to this setting. Okay, so I set up this notebook where I load this data from the study. Okay, so let's visualize it. Okay, so it's gonna have 4 entries: first name, gender, the race that is used to determine the first name, and whether or not the resume received a callback. Okay, so for the name and ATE, the name and variance, and confidence intervals, I'm going to write a few functions and let you apply them in the discussion worksheet. And in the lecture video, I'm going to focus on the Fisher-Zect test, okay, because that is going to be slightly more tricky. So what am I going to do? Okay, so first let's just see, let's see that we have an equal number of black names and white names. Okay, so this is based on the randomization that the authors did. And now let's do a cross tabulation. Okay, so you can do so using the PD crosstab function. And I'm going to select the columns with race and the columns that corresponds to the outcomes. So this is whether or not they got a callback. Okay, and we get our 2x2 contingency table as so. All right, and I think in this case it's flipped compared to what I said and what I wrote on the note. So let me just do it this way. Okay, so success or failure is going to be in the rows, and then the treatment is going to be in the columns. And now we can run Fisher's exact test. Okay, and we do this by importing from SciPy stats. Okay, so let's see what this function does. It takes as input the table, and whether or not you want to do a two-sided test or one-sided test. Okay, so let's just do a two-sided test because why not? Okay, so it's simpler. And let's see what the output is. Okay, so the output is an odds ratio and then the p-value. Okay, so we defined what odds ratios were in the previous lecture, but let's not care about them. Okay, so I'm going to put a dummy variable here, and p-value is equal to Fisher's exact test. And I'm going to call this table. Okay, so let's do this. And voila, we get a p-value of 4.8 to the 10 to the minus 5. Okay, so what is this? This is, okay, so this is very small. Okay, so you can see that this is going to be less than 0.00, so 5 digits, right? 0.00001. Okay, so it's really tiny. Okay, so this gives you evidence that there really was racial discrimination. And just to show you the table again, okay, so you can really see from this that the white resumes got more callbacks. Okay, so there's really some difference, and we just wanted to know whether this difference was due to noise or whether this was statistically significant. Okay, and by computing the p-value in this way, we conclude that it is indeed statistically significant for the Fisher-Sharp null hypothesis. Throughout today's lecture, we have been talking about how to think about causality in terms of counterfactuals and potential outcomes. So this framework is actually called the Neyman-Rubin framework, and is due to these two gentlemen that I'm showing on the slide. Okay, so Jesse Neyman was the founder of our stats department here at Berkeley, and you probably have already heard his name several times in this course. Okay, and Don Rubin, I think you've seen him before as well. I think we talked about him while we were on the topic of posterior predictive checks. Okay, so this is giving credit to the people who came up with this framework. And let's now summarize what I've learned about how to do inference under this Neyman-Rubin framework. Okay, so first, this framework does not require any modeling assumptions on the potential outcomes. Okay, so we didn't assume any GLM, linear model, or any other model for that matter. The y sub I ones and y sub I zeros were just numbers. Okay, they could take any value. But however, even though we don't make those assumptions, this framework is not completely model-free. We still have to make the Sutva assumption. Okay, but at least the assumptions are minimal. Okay, and this is a frequentist framework. Okay, so if you're being Bayesian, we have to have some kind of model. In this case, you don't really have a model. And the randomness, contrary to how we usually think, even from a frequentist perspective, does not come from sampling. Instead, it comes from the design of the experiment. Okay, so the randomness is in the random assignment to units to either treatment or to control. And this randomness is under our control as opposed to in other settings for frequentist inference. Okay, and then causality is formulated in terms of instances. Okay, so we have this notion of individual treatment effect, but when we want to estimate anything about causality, we can never think about individuals because of this fundamental problem of causal inference. And instead, we estimate it in terms of a class. Okay, so what happens on average to all the people in this study. Okay, so in other words, we focus on the average treatment effects. Okay, so this also means that if there's some heterogeneity, so if different people have different individual treatment effects, then this is unaccounted for, okay, because we only think in terms of averages. Okay, so in recent years, people have been focusing more on heterogeneity, but this is sort of an advanced topic that is beyond the scope of our class. Let us now talk about some complications with randomized experiments. Okay, so randomized experiments are the gold standard. Randomized experiments are often considered the gold standard for causal inference. And many people also think that randomized experiments are the only way in which you can make rigorous causal conclusions. Okay, so in the next lecture, we're going to talk about how to think about causation when you move away from this setting. But apart from that, there are also some complications that can happen when you work with randomized experiments. Right, so in this video, we'll talk about two such complications. And the first one of this is compliance. Okay, so what's compliance? Okay, so this is the observation that when you do experiments and you assign people to treatment or control, the individuals in the study may not actually be obedient. So they may disobey you and they may not comply with the assigned treatment. Okay, so here's an example. Okay, so medical trials are randomized experiments, and in such a trial, we assign some patients some treatment A, and we assign other patients treatment B. Okay, so sometimes this is double-blind, sometimes it's not, and patients may actually decline the assigned treatment sometimes. Okay, so this is so if it's not double-blind and they're asked to get randomized into the surgical arm of some trial, some patients might actually disagree and not want to go for surgery. And even if the trial is double-blind, sometimes the drugs that patients assigned to take might have some side effects that are unpleasant. So some patients might just stop taking the drugs. Okay, so that's one example. Here's another example. Okay, so previously we talked about this Oregon health insurance experiment that randomized people into being enrolled into Medicaid or not. And it turns out that for those people who won the lottery, who were randomized into being able to enroll, only 45% of them actually enrolled. And on the other hand, for those people who lost the lottery, in the sense that they didn't get that chance to enroll in health insurance, 18% of them actually ended up enrolling. Okay, so maybe they found another way to enroll in health insurance. All right, so in essence, there's a huge number of people here who did not adhere to their assigned treatment. Okay, and if that happens, then we sort of have the question about whether the treatment effect that you measure, okay, so you can still compute the ATE and all that stuff, but then the meaning of it is going to be a little bit distorted, okay, because only some people who get assigned treatment end up actually taking it. Okay, and another way in which randomized experiments have problems is this idea of external validity. Okay, so what's the problem here? So recall that when we define the ATE, it's always with respect to a fixed experiment population. Okay, so where does this population come from? If it were a medical trial, the center that runs the trial is going to have to search for patients that meet certain criteria. And even for other experiments, so we saw a lot of social science experiments, somehow the population has to be selected. Okay, so there's some selection, there's often some selection criteria, which means that the population that we end up with for our experiments may not actually be representative of a larger population that you are actually interested in. Okay, so here's an example that isn't actually from causal inference, but in spirit, it demonstrates what the problem is. So in the 2016 US presidential election, most polls, a huge majority of them, showed sort of predicted that Hillary Clinton was going to win by a huge margin. Okay, and so famously this was false, and she didn't win. Okay, and so what was the reason behind this? Okay, so polls are not perfect. They always have, because they are based on samples, so there's definitely going to be some error. But this was a huge systematic error, and the reason was because of this idea of external validity. Okay, so how do people do polls? They call up potential voters or people who are part of the voting population and ask them whether or not you're going to vote for some candidate. And so we have this notion of the sample population that's being polled. And it turned out that this sample population was very different from the voting population. Okay, so for instance, it was observed that people who were more likely to vote for Trump were also less likely to answer the phone. Okay, so the people who ended up being called and being polled was different from the entire voting population. And this meant that the results of the polls became even beyond sampling error, was just not representative of the entire voting population. Okay, so similar things might happen for randomized experiments that are conducted in different settings.